Hey everybody, this is Larry. Hit the like button, hit the subscribe button. Let me know how you doing this problem. I'm gonna solve it live right about now. Um, 691 stickers to spell word. We're given n different types of stickers. Each sticker has a lowercase English word on it. You'd like to spell out the given target string by cutting individual letters from your collection of stickers and rearranging them. You can use each sticker more than once if you want, and you have infinite qualities of each sticker. What is the minimal number of stickers you need to spell a target? If the task is impossible, return -1. Uh, hmm. My intuition is greedy, but I'm trying to figure out why that wouldn't work. Oh, stickers. Let's look at the constraints a little bit first. No, I mean greedy definitely doesn't work. I think I was thinking of cuts maybe and not the stickers, because in this case, like, you could have use two from this word or three and then one from this word and then some, like, combination which makes it, I don't know, which makes it interesting. But let's look at the constraints. I think there may be some dynamic programming-y stuff. Stickers is in the length of 50. Target has length in the range 1 of 15. In all test cases, all words were chosen randomly. Okay, that's fine. Time limit may be more challenging. Is expected a 50 sticker case can be solved with. Okay, I mean, I don't care. So there's definitely a dynamic programming problem with the subset. It's one of the subset dynamic programming ones, which you can solve with. I mean, because the big thing to notice is that n, where n is the size of the target, is only up to 15. So the number of states is 2 to the 15. And then the number of subsets of those states is also, it will make it like 3 to the 15 times 50, maybe something like that. But then we can, maybe that's a little bit slow, but then we can pre-calculate what each sticker does. So then in that case, maybe that's better. But 3 to the 15 is a little bit, 14 million maybe is a little slow, but I guess we'll see. Yeah, I'm going to kick off by doing that, and then see if we need any more optimizations. I think it's roughly right, but some definitive roughly. So we have to do, first of all, we're going to start with the pre-calculation. So basically what I want to do is, for each sticker, I guess that's actually not. Well, let me. How would I want to do it? There's still a lot of combinations, so maybe I. And each sticker can have multiple whatchamacallit. So that's actually a little bit tricky, maybe. I mean, it's still true, but just trying to prank. I think I'm just trying to optimize the worst case in my head, which is kind of a little bit tricky. Yeah, I mean, I think the problem is basically saying that, okay, like, you have the word the hat. You want to get T from one of these stickers and then letter H from one of these stickers, but each sticker can satisfy multiple letters, so you want to do that with the minimum amount of stickers. Yeah, exactly. A sticker is like a bag of letters. I don't know, that phrasing just sounds funny. Also, hey, what's up, Bobbins Talk? But I'm just trying to do it I mean, I think like, I don't think you could. Yeah, and I'm just trying to think about like what is the best way to do this in a brute force way, because there's 2 to the 15 states, so that's not that bad, I think. But that's only 32, um, but oh sorry 32,000, but each of those states may do a lot of work. I'm trying to figure out the right way to pre-calculate that so we can make the work a little bit easier. Um, I guess maybe that's fine, to be honest. Given a string. I think in my mind, I'm just trying to think if there's some sort of ordering that we can impose on this, so that we can kind of terminate early or stuff like that, or just take advantage of it in general to kind of improve some movement. So I definitely want to sort this. Does that work on a string? Yes, it doesn't really matter. But, okay. Actually, I'm just curious whether this works on a string. I need to be better about Python, but okay. So you don't get a string back, but so it does get sorted, which is fine. Okay. And then now for each, we want to do the same for each of the stickers. And then now, now we want to pre-process the stickers to use that always has. So one constraint I want. So one constraint that I want to impose is that we always want to at least remove the first letter of the target. So that way we don't just do like very naive recursion. In that case, for each letter on this target, we can just see which sticker uses it, and then we could kind of go from that. Okay. So for character in target, and now for sticker character in stickers. I guess sticker in sticker, and for sticker character in sticker. I guess I could just do if C is in sticker, then let's put that in a lookup table. What's it called? I guess we'll just call it lookup. Okay. Yeah, whatever, just call lookup. I'll fix it later if I need to. Collections are thick of default thick of list. If C is in sticker, then that's okay. We actually want to we don't want to actually put in the sticker. We want to put in the index for a little bit of performance reasons. So let's just do lookup.append I. Okay. Okay. So now do like a letter dot product word. Okay. So now we just have to we do a recursion stuff. Go and then now we just go Oh, let's just say best of, or get best of, it's a very generic term. 1 to the n, okay. Okay. And let's just start with 0. Oh, and actually this is this minus 1. 0 being the first index of the string. And this actually don't have to cache as a result. Actually, this may be a good time for me to learn how to use LRU cache. I've been talking about it for a while. So I could just do it. I'm just looking up real quick. I did like. Okay, so I just need to do this. Right? Okay. Oh, thanks. Thanks now too. Yeah, I just googled it. But okay. Let's just say index and then the bit mask. And then now, and the index is based on a bit mask. So if bit mask is equal to 0, that means we're done. And then we return 0. That's one of the base case. Man, this feels so easy now that I have LU cache, because I'm like, my mind goes through my checklist for writing DP, and some of that is like, well, now I have to look up the cache and stuff like this, which I don't have to do anymore, obviously. But yeah, and then if another base case is if bit mask and 1x is equal to, if this is equal to 0, that means the bit mask doesn't include this index, so we just return get best index plus 1 bit mask. Technically, you don't need this. It's just for me to maybe easier look up for. Otherwise, you have to do a for loop to get the first bit that is a 1. So I don't know. I don't know if this is that much better, to be honest. But it makes some of my coding a little bit easier at the cost of, well, in this case, space. Actually, this is maybe a bad time for LRU cache as a result, because in this LRU cache, it would cache the index plus bit mask. But actually, what we want is just caching on the bit mask, if that makes sense, because bit mask or index or bit mask implies index in this case. So you don't. It's not part of the key. Even though it's there just for my shorthand programming reasons. Hope that makes sense. But thanks now too. You are right. And at the end, well, let's just go through it then. Mask. Let's use, well, best isn't 0 because you want a min. So let's just call this infinity. And also, I think there's a -1 somewhere. So let's just say if is greater than or equal to infinity, then just return -1, return results, and then that's actually set infinity is 1 to 60. Okay, and then now let's using the lookup table, and maybe this was a little bit premature optimization, but yeah. So okay. So now we have target of index, and oh yeah, I guess another case is if index is equal to n, then we actually have to return infinity, because in this case, the bit mask is not 0, which it should be. Okay. So these target sub edge or target sub index is, what is that? Oh, that's the first character, and in that first why did I do that? Okay, there you go. So then now the lookup table of this will contain all the stickers that we want. But then now it's a little bit, there's a lot of coding in a bad place. Oh yeah, Math to Infinity, you're right. Right, I keep on forgetting that because I think, because that's like newish, right? But okay. Yeah. I mean, I know I could just, but yeah. Okay, so for sticker index in this lookup table, we want a recursive on it. So best is equal to min of best and then some recursion thing. So index plus 1, I guess. And then some new bit mask, right? That's kind of like the logic. But how do we construct this new bit mask, right? I know that's not what you meant, but I don't want to just fix all the code in different places. But okay, so new bit mask is equal to using the sticker, and then can I do this more efficiently? I feel like I'm doing this in a little bit not great. Especially in this case where you may use the same letter multiple times, and it's a little bit trickier to handle. And that's kind of why I'm hesitating a little bit. But I guess we just have to do it. Let's do it naively, and then if we have to optimize it, we have to optimize it, and we'll figure it out. But what am I doing? We're given the sticker index. The sticker is equal to sticker index. Okay, fine. So for character in sticker index or sticker, is this is n squared fast enough? I worry that this is gonna be a little bit costly, but okay, let's just call new bit mask is equal to whatchamacallit, bit mask for now, and then for each character in sticker we find it in whatchamacallit, in the current target. Okay. If define is greater than 0, then okay, let's just put it in a variable so we don't do it again. So if we find it, let's just do if we do find it, then new bit mask. We have to do it another way too. Okay, I can just use find, because we have to do it for target character and target if target index. If C is not equal to C, continue. Otherwise, if new bit mask is a 0, then we continue because we drew it. Okay, new and T index is equal to 0, then we continue. Otherwise, let's mark that out. Uh, is that right? Okay. And then we can break. Okay. Maybe that's it. We'll see. Okay. Well, at least it resolves. Let's see if this gets -1 correctly, actually, just for funs. Maybe, well, it definitely doesn't work because I don't have a +1 somewhere. So that's probably why. It actually is this +1, I think. That's just silliness. Okay, let's see if that works. Running time, I don't know if that's good. Well, I guess we could test one real quick. Hey, what up, Mbrax? How are you doing? Okay, I'm lazy, so let's just do that. What's the running time here? I know, but this is not the language. I'm just trying to get a running time estimate. Oh, huh. Why doesn't my output? Okay, but the test case seems to be It's always funny when my thing is way more performant than their code for whatever reason. 16, 24, 32, 40, 48. But okay, I mean it's slower, but we'll see. Okay, let's just submit. Maybe it's still a little slow, but I'm a little bit lazy. At least correctness is okay. Maybe. Okay, cool. It's not that fast at all. I probably could have done some optimizations. I mean, I could have pre-calculated this a little bit better, to be honest, and maybe even cache it, just to be frank, because there is probably some. I mean, there is definitely no, because for a given bit mask, this only execute once, so maybe that actually doesn't make sense to be compute. But yeah. Hey, what's up, UK gang? No, I mean, these are just like test cases, right? And I just wanted something. I was too lazy to construct something real. I just wanted something that at n is equal to 15 and the number of stickers is close to 50, just to kind of see my running time. Like I knew it was gonna be the right result. Well, I mean, at least my code runs, and even though the system test code doesn't run, but I just wanted to get the time result is kind of one of the worst case. That's why I constructed that. But overall, what was I going to say? Yeah, I mean, I think some of it is that I'm not necessarily sure on how to optimize or how much to optimize. I guess in theory, maybe, I mean, I definitely did things a little bit on the slower side, on the 700 millisecond. But maybe I could have done this in a different language and that would have been way faster because definitely Python is slower and stuff like this. But so I'm glad that I did this thing because, well, maybe not this, but I did this instead of using our LRU cache because that would have definitely been too slow because it multiplies it by another dimension of the state. But hey, what's up, Tux? How you doing? But yeah. You got here at the right time because I'm just about to go over it. I'm just trying to, like, I just solved this literally like a few seconds ago, maybe a little bit before a few seconds ago. How long did I take on this? About 25 minutes. So I think I don't know how much explanations I did. So, but I feel like that's about right. 20 minutes me programming this. I need to be faster on something that, to be honest. I need to practice being faster on stuff like this because I knew how to do this almost immediately, but I still kind of linger a little bit slow. Maybe not right now, but like during contests, because I feel like like you know how to do it, then you should have done it faster. Like for me, I'm talking to myself. But yeah, for this problem, I think the first thing kind of, I mean, I don't know if there's a better way. I think one thing to kind of have in your repertoire is kind of think about just like what is the worst case. And for me, the first thing that I was like, well, this feels a little like I don't, to be honest, I don't have a strict proof, and maybe there's another algorithm that's polynomial that solves this. But for me, I was like, okay, this feels a little like some sort of going to be like an NP problem type thing. So from that, I was like, okay, well, it's either backtracking or dynamic programming or something like that. So then first thing I was like, okay, let's look at the constraints of the problem, right? And the constraint in this case, I think I was way articulate on this one. Well, not like I just talk a lot during this one, maybe not articulate, but where I noticed that n is equal to 15, and from that, the idea is maybe I could have done this. I could have tightened this a little bit better. But the idea here is that with n is equal to 15, and you want to get all of them, that means there are only 2 to the 15 possibilities, which is like 32,000, as I mentioned in the beginning. So then I knew that that would be the state, and that would be good enough because that's, or well, I know that it'll be good enough in terms of memory usage, because 32,000 numbers or whatever it is, plus the key, I guess, it's really not that much, right? So I knew that that was going to be good in space. I think I spent a bit of time thinking about the time collection, because definitely with what they call subset string type things, you can definitely get into a thing where it ends up being 3 to the 15 or something like that, or 3 to the n, which is 3 to the 15, which is cutting it close. I think it was like 14 million or something like that. But and then I have this thing where like I'm not super happy about, where like basically this is a very naive algorithm, and maybe I could have optimized it a little bit better. I'm trying to with slightly different representation, but I just basically did a n square where n is 15, or I guess n times m where it's a sticker length, but there's also like a lot of potential stickers. I did do an optimization where I always given an array, given a target, you need to get every character anyway. So you always want to use so every character needs to be used once, which for me I took it as always. All right, only consider stickers that removes the first character, so that I can kind of prune that state more, because you need to do it anyway, but that imposes some sort of ordering on the dynamic programming, or additional ordering, which does not change the answer, but it should improve us in terms of speed a little bit. So that's kind of how I thought about it. And then here is just it's just matching the character in a sticker with the character that we have, or the characters that we need from the target, and then just flipping them off. And then here it just, well, goes to the next index, and then we have the new bit mask using this sticker, and then add 1 for using 1 sticker. And that's kind of the recurrence for this dynamic programming. And as I mentioned earlier, the index plus 1 actually doesn't do much. It just allows me to keep track of the first index in the bit mask. It's just a little bit of a programming hack, if you will, but it doesn't really change the state. And that's why I didn't use the LRU cache, because index depends entirely on bit mask, and because of that, it is sufficient that we cache the bit mask and not the index. How do you, yeah, well, I'll get into that in a little bit, but let me finish writing this. You can match wildcard. Oh, I guess Ambrax is answering your question then. Yeah, let me focus on this problem for an extra second, an extra beat. And then let me think about it. Is that what I want to say? So that's just an explanation of the problem. And again, it is probably it is. It actually doesn't tell me how long each of the sticker word is, but each, let's say the number the length of a sticker is the same as the target, which is 15, and we'll denote it with n. Then in this case, it will take n squared times 2 to the n times m, where m is the number of stickers in the complexity. And in space, it is just 2 to the n, where n is the length of the target. I do a little bit more, but 2 to the n should be the dominating one. You could say 2 to the n plus n if you want to, but which in theory, I guess, doesn't really matter. Also do some sorting. The sorting actually, looking back, is not that necessary, but I think it just helps me, well, it's not necessary, but it makes this part slightly faster because they're sorted, so you can kind of, so you could actually, in theory, do a 2-finger algorithm to kind of make this part go faster after it's sorted, actually, now that I think about it. But I didn't do that, so, and it turns out to be not necessary. But yeah, in terms of interview, I mean, this is a very hard problem for an interview. Maybe, I think if you do get this on an interview, more than likely it's meant to be like a more open, like you probably generally don't get these kind of constraints in an interview. You just have an open-end problem, and then you kind of discuss like, okay, with n is this, we have this algorithm and so forth. Because I think in general, this is like one of those like really hard problems, like computationally. So you would probably just talk about like branching and bounding and how to kind of make it easier to do exhaustive search. Maybe even talk about approximation algorithms and stuff like this. But yeah, in terms of competitive programming, I think so. The bit mask thing does come up sometimes from time to time, and it is something that kind of forces you to kind of look at the constraint and look at how much you could get away with these kind of dynamic programming problems. I think I actually talked about this a little bit earlier with the problem that was on the contest yesterday, where a similar thing. I think bit mask problems are not that common in general, but once in a while they come up. So yeah, what is the hint? I'm just curious about hint. Oh, that makes sense actually. Okay, so apparently the answer maybe is just exhaustive search, and I just did it with DP, with dynamic programming. But yeah, that also makes sense. Okay, that would actually speed it up. But that's not like a worst case. Like it doesn't optimize your worst case. It just makes your average case better, probably. I was thinking about it similarly actually, but yeah, makes sense. Okay, cool.